This is Jack Creel, and I'm going to be explaining Ben Costa's analytical questions and solutions. So question 1 goes over topics 2, 3, and 4, and it states that there is a raft floating in a hot spring with water at 200 degrees Celsius and a weight of 100 kilograms. On the raft, there's a barrel of mercury with a specific gravity of 13.6. The barrel has a height of 1 meter and a diameter of 50 centimeters. And it asks how much water is displaced by the raft in the barrel, assuming the barrel is open to the atmosphere. And then assuming that there is a hole at the bottom of the barrel with a diameter of 1 centimeter, find the initial acceleration. So the first step is just going to be to draw a diagram and define our system, which is going to be comprised of the combo of both the raft and the barrel. And then we'll assume that the raft is initially at rest, it's not moving to start, that both the mercury and the water are incompressible fluids, that there's no friction in the barrel or any shear forces acting on the raft, which might not be completely accurate in reality, but for the scope of this course, those are completely fine assumptions. And then we'll need to find the density of water at 200 degrees Celsius, which we can get from our handouts, table A9. And then we'll use a density of 1,000 kilograms per cubic meter when talking about the specific gravity to get the density of mercury. And then we'll assume that the hole is at the bottom of the barrel and that there is no work done. So to start, we know that at equilibrium, the buoyant force acting on our system is going to have to be equal to the gravity force. And so we have our gravity terms over here and the terms that go into the buoyant force over here. And then all that's left there is just to rearrange for the displaced volume of water, and we'll get a value of 1.1 cubic meters of water has been displaced. For part 2, to find the acceleration, the first step is going to be to get the velocity of the fluid coming out at point 2, which is going to be the bottom here, and point 1 will be the fluid at the top of the barrel. So we'll write out the Bernoulli equation. We know that at the top of the barrel it's open to atmosphere, so we can cross out that term. We know that the fluid at the top of the barrel is going to have negligible velocity, so that one goes away. We've already assumed no work. The hole is also open atmosphere, so the pressure at point 2 goes away. We're going to set our coordinate system so that the bottom hole is the bottom of our system. Z will be 0. And then again, we've ignored work and loss here. And then to rearrange and solve for the linear velocity of the fluid at point 2, we can get a value, and then we'll be able to use that value to find the acceleration it causes in our system. So we'll start with a momentum balance, which is of the general form in minus out plus generation equals accumulation. There's no inlet stream. We've assumed there's no shear forces. We don't have any other forces acting on our system, so we can ignore that. And then for our accumulation terms here on this side, all that we know is that since we're just talking about the initial acceleration right at the beginning here, we don't have to worry about the mass of our system changing at all. So we can cross that out. And once we plug all that in and rearrange for acceleration, all that we will need to find is the mass flow rate of the fluid here. And to do that, it will be the volumetric flow rate times the density of the mercury. And we already have the linear velocity, so all we need to do is multiply that by the area of the hole and the density of the mercury to get the mass flow rate, and then we're good to plug everything in and solve for acceleration. And we find that the system will initially accelerate at 0.0076 meters per second per second. The second question is going to cover topics 1, 3, and 4. And so we have subcooled water at 45 degrees Celsius traveling through this piping system here. A pitot meter is used to measure the velocity of the fluid, and we need to determine the gauge pressure, the velocity, and the volumetric flow rate through the pipe. So again, we'll start with a diagram. We'll have point 1 here and point 2 here, and we will assume that there's steady flow through the piping system, that it is an incompressible fluid, pretty common assumptions that we're going to use again, and then that this system is subject to atmosphere, so there's atmospheric pressure here and on the outside. And then again, we're going to assume no friction and no work. So to find the pressure, as a first step, we're going to use the rho GH equation. The height is going to be the height of the fluid column here, the density of water, and then gravity. And we can find that the pressure in here is going to be 19,623.8 pascals. The next part is going to be to find the linear velocity, again at point 1 here through the system. And so we'll set up a Bernoulli equation, and we'll go through with what we can cancel out. We are going to set this again to be z equals 0. That'll be the bottom of our coordinate system, where we've assumed that there's no work. And then we've assumed that this is open atmosphere on the outside. So at point 2 here, that's atmospheric pressure. That's static right there, so there's no velocity. And again, we've assumed no work, no losses. So then, again, we're just going to rearrange and solve for the linear velocity here at point 1 with all those terms that we already have. And then we can use the linear velocity for the last part to find the volumetric flow rate just by multiplying it by the area. And we'll find that the volumetric flow rate is 0.54 cubic meters per second.